This is a summary video for the C3 Quantitative Chemistry Unit for the AQA Separate Chemistry Award. In this video we will cover all the content required for both foundation and higher tier. During this video we will look at the topic question, how is mass conserved and how can reaction masses be calculated? Looking at picture A then, 5 grams plus 5 grams would give us a total of 10 grams. On picture B, 1 gram plus 8 grams gives us a total of 9 grams. On picture C, what number would we need to add to 5 to get to 8 grams? That would be 3 grams. And then finally, what number would we need to add to 9 to get to 20 grams? That would be 11 grams. And what each of these pictures illustrates is the total sum on the left hand side is equal to the sum on the right hand side. The pictures we've just seen are important because we can apply this to chemistry, where the total mass of the reactants is equal to the total mass of the products in any reaction. This means mass is not created or destroyed in the reaction, and we call this the law of conservation of mass. This can be employed then in examination style questions. So here we see that with titanium chloride it reacts with sodium to produce titanium and sodium chloride. In the reaction it tells us that 1140 kilograms of titanium chloride completely react with 552 kilograms of sodium. This produced 1404 kilograms of sodium chloride, and the question then asks you to calculate the mass of titanium produced from this reaction. As you can see, this is a 1 mark question, so we're not looking for a complicated calculation with this. So in tackling questions of this nature, annotate the question with everything that you know. Check that your units are the same, highlight what's missing and rearrange to find your unknown quantity. So here I know that I've got 1140 kilograms, so I'm going to annotate my equation with that, and I can continue with the mass of sodium and the mass of sodium chloride. I now know, due to the conservation of mass, that the sum of both sides must be the same, and I'm calculating the mass of titanium. This gives me the equation shown, so 1140 plus 552 is equal to x, that's the one thing I'm trying to find out, plus 1440. So I can rearrange this equation to find x, and my final mass is 288 kilograms of titanium. Looking at the video that's showing on the right hand side, what can you observe? So that means what do you see, what do you think is happening, and what do you think the iron is reacting with? Well, the reaction that we're seeing is the reaction of iron and oxygen to form iron oxide. Oxygen from the air is reacting with the iron. And we can balance the equation to show that 4 atoms of iron react with 3 molecules of oxygen to form 2 molecules of iron oxide. Because we'd originally started with the iron, if we did this on a balance, it would appear that mass had increased because the oxygen is adding to the iron, and when they combine you are adding 2 masses together. the mass would appear to increase because the product iron oxide contains all of the atoms from the iron and the oxygen. So we would need to add the masses of the iron atoms and the oxygen atoms together. And this would show us then that mass had been conserved. So here we have a different reaction, and in this reaction, were we to do it on a balance, it would appear that mass had been lost. Why do you think that might be? Well, in this case, hydrogen gas is produced. So if the gas was able to leave the reaction, i.e. if it didn't have a lid on it, then that mass of hydrogen would appear to have been lost. Let's look in a little bit more detail at masses then. So first of all, we're going to look at relative formula mass. So first of all, let's remind ourselves about chemical formula. The formula will show us the type and the number of atoms that are bonded together to form a molecule. So in our molecule of methane, you can see that there is a carbon in the middle and there are 4 hydrogens bonded to that carbon. And if we were to write the formula of that, we would write that as CH4. We've got 1 carbon and the 4 appears directly after the hydrogen to show us we have 4 atoms of hydrogen. We can do that then for carbon dioxide, something you're quite familiar with. That's 1 carbon and 2 oxygen. And finally for water. It's really important that we use subscripts for writing these formulae. If we don't, you will lose easy marks. So when we calculate the formula mass of a compound, what we do is we add up the masses of each of the individual atoms in the molecule. So here we have ammonia and its formula is NH3. We've just seen that that tells us it's got 1 nitrogen and 3 hydrogens. So if we were to work out the formula mass of ammonia, then we need to add 14, which is the mass of nitrogen, plus 3 times 1, because 1 is the mass of hydrogen and we have 3 of them. If we add that all together, we get a formula mass of 17. We can do the same for sodium oxide. So in this case we have 2 sodium atoms, so that's 2 times 23, and we have 1 oxygen, which is 16. So we add 2 times 23 plus 16, we get an answer of 62. So they're quite straightforward. But then we have formula with brackets in. So in this case, the first thing you do is work out what's inside the brackets and then times it by the number outside of the brackets. So using this example, we've got 24, which represents the mass of magnesium, and then this small 2 outside of the brackets now comes in front of it, and inside of the brackets we would have 16 plus 1, 16 being the mass of oxygen, 1 being the mass of hydrogen. We add all that together, we get 58. We do the same for calcium nitrate then. This one's a little bit more complicated. 40 would be the mass of calcium, and then we have inside of the brackets we have 14 for the nitrogen, and we have 3 times 16 because there's a 3 directly after the oxygen, but then all of that added together needs to be times by 2 because there is a 2 outside of the brackets. Sometimes we might want to know what percentage of a compound is made up of a particular element, and this is called the percentage composition by mass. Because it's a percentage, we are going to be multiplying our fraction by 100. So the number of atoms of whatever element it is that we're trying to find out times the atomic mass of that element, and then divide by the formula mass of the compound. So let's have a look at a worked example. Here we're going to calculate the percentage of oxygen in carbon dioxide. So the formula for carbon dioxide is CO2. This tells us that we have 2 oxygen atoms because the 2 is directly after the O. Each oxygen atom has a mass of 16. And the total formula mass for carbon dioxide will be 12 plus 2 times 16, which gives us 44. That's all the information I need to know to work out the percentage of oxygen in carbon dioxide. Let's do the calculation then. So I have 2 atoms of oxygen times the atomic mass of oxygen, which is 16, divided by the formula mass of the compound, which is 44, and then to turn it into a percentage I multiply that by 100, and that gives me 72.7%. The following content is for higher tier students only and will not be examined on the foundation paper. We're going to look at moles, and not the brown furry ones, but a chemical mole. First of all, what is a mole? So if we asked you how many goals Tammy Abraham scored, if he scored a hat-trick, you all know that that would be 3. And on the right hand side then we have 1 dozen eggs, and you would all know that that would be 12 eggs. Well, a mole's not very dissimilar to that. Avogadro proposed that equal volumes of all gases contain the equal number of molecules. Now, he wasn't able to prove that, but sometime later somebody else proved that he was correct. So Jean-Baptiste Perrin found that not only was Avogadro correct, but he was also able to put a number on that. So he found that if you weighed out the mass of any atom in grams, it would have the same number of atoms in it. So for example, if I weighed out 12 grams of carbon 12, then I would have 6.022 times 10 to the 23 atoms of carbon. And you can do that for any element. And we call this a mole. So now we know that a mole contains 6.022 times 10 to the 23 atoms. But why is that important? Well, here I have an equation where 2 moles of magnesium react with 1 mole of oxygen to produce 2 moles of magnesium oxide, and that's what those large numbers before signify, that they signify moles. Now if I just weighed out 10 grams of each of these, I wouldn't have the right number of atoms to react. However, if I weighed out the mass for 2 moles of magnesium, which would be 48 grams, and the mass for 1 mole of oxygen, which is 32 grams, then I would have exactly the right number of atoms to completely react. Now we can calculate moles using this equation. So MR, that's the formula mass, times moles equals mass. I like to think of it as Mr. Moles equals mass. It's a nice way to remember it. And if we use that equation, we can work out for any given mass how many moles of something we could have. So in this first example with water, we have 36 grams, and I need to know how many moles of water that is. So first of all, I work out the formula mass like we've previously done, and then I divide my mass by my formula mass, which will give me the number of moles. So when we are asked to do these types of equations, the first thing to do is to work out the formula mass. Then once you've worked out the formula mass, you can divide the mass by the formula mass to get the number of moles. Now we know how to work out the number of moles, let's have a look at a chemical equation. So here we have the equation to make ammonia. And if I react 1 molecule of nitrogen with 3 molecules of hydrogen, I make 2 molecules of ammonia. That ratio is fixed. So if I had 12 nitrogens, I would need 36 hydrogens and I would produce 24 ammonias. I can use different numbers, so I could put 1 dozen. It's still a 1 to 3 ratio, so I'd need 3 dozen hydrogens and I'd need 2 dozen ammonia. If we're looking at the number of atoms, you can see huge numbers, really difficult to put into our calculators, and we were doing calculations with these long before calculators were invented. Hence we use the term mole. So I've got 1 mole reacts with 3 moles, reacts with 2 moles. You'll see in each of these the ratio of atoms remains the same. So sticking with this equation, 1 molecule, 3 molecules, 2 molecules. And we've still got the ratio 12, 36, 24. However, sometimes you will only know one of the values and you need to calculate one of the others, and they're not always straightforward whole numbers. So how would we approach something like that? Well, let's take the example that we've got 1.75 moles of hydrogen and I need to work out how many moles of ammonia that would produce. So we need to be able to use this ratio 3 to 2. So I know that I've got 1.75 and I need to work out the moles of ammonia. So using this arrow, you can see that when I've got 3, I get 2. So when I've gone from 3, and I can put 3 on the bottom because that's what I've come from, and I'm going to 2, 2 goes on the top. That gives me the fraction of 2 over 3. If I then multiply 1.75 times 2 over 3, that would tell me that the moles of ammonia that I would make are 1.16. So we can use this when working out reaction masses. So what mass of titanium chloride reacts with 460 grams of sodium? Well, first of all, I like to draw a table. I think this helps you to get the information out of the question and easily see what it is you're trying to calculate. So from the question, it told me that I had 460 grams of sodium. Because I can work out formula masses, I can also fill in my MR row. So sodium has an MR of 23. Notice at this point I have not multiplied by 4. I am only interested in the atom or the molecule, not the number that goes before it. Titanium chloride, if I work out the formula mass of titanium chloride, so 1 titanium plus 4 chlorines adds up to 190. That's great, because what that now does is it shows me that for my sodium I know 2 out of 3 of my values, so I can calculate the third one that I don't know. So my moles of sodium is equal to the mass of sodium divided by the formula mass of sodium, which is 460 divided by 23. That gives me an answer of 20 moles of sodium. So looking at what we've just done with mole ratios, I can now work out the moles of titanium chloride. And the way that I do that is I have my arrow, so I know the sodium, so I start at the 4 and I'm going to the titanium, which doesn't have a number, so that means it's 1. So from goes on the bottom, that's a 4, and I'm going to the titanium, that goes on the top. So I now need to multiply my number of moles by 1/4, which gives me 5 moles of titanium chloride. That's fabulous because now I know the number of moles and I know my formula mass. I can work out the mass of titanium chloride. So the mass is equal to MR times moles, Mr. Moles equals mass, which equals 190 multiplied by 5. So it gives me a total mass of 950 grams. So in answer to my question, what mass of titanium chloride reacts with 460 grams of sodium, the answer is 950 grams. This is quite a complex calculation and in any exam would be worth 4 marks. So well worth learning how to do these. Let's have a look at another one then. So the mass of oxygen needed to react with 10 grams of calcium to form calcium oxide. Well, again, we draw our table and we take the information that we already know from the question. So we knew there was 10 grams of calcium. We know that the formula mass for calcium is 40. Remembering I've not multiplied that by 2, that comes in later. And then the formula mass for oxygen, O2, is 32. So this time I do use this 2 because that's part of the molecule, but this just says I've got 2 atoms of it. So now I can work out the moles of calcium. That's the thing that I've got 2 out of 3 for. So first of all, I work out my moles, and you're always going to be working out the moles of something first. So my mass over MR to calculate my moles, 10 divided by 40 gives me number of moles of 0.25. Working out what I do with my ratio then, I'm going from 2 to 1. From goes on the bottom, 2 goes on the top. So I've gone from 2 to 1. So my moles of oxygen is 1/2 times 0.25, which is 0.125. And then final step, I now for my oxygen know my moles, I know my MR, so Mr. Moles equals mass. 32 times 0.125 gives me an answer of 4 grams. Let's now look at concentration. This topic is appropriate for both higher and foundation tier students. What does concentration actually mean? Do we know how many centimetres there are in a metre, and therefore how many centimetres cubed would there be in a metre cubed? Well, concentration is the number of particles per unit volume. In a metre there are 100 centimetres. So if we're working out centimetres cubed in a metre cubed, to work out a volume we multiply each of the sides. So it would be 100 times 100 times 100, which is 1,000,000 centimetres cubed in a metre cubed. So thinking specifically about particles then, here I have a picture of a concentrated acid. It's got lots of acid particles dissolved in it. If I compare this to a dilute acid, you can see there are only a small number of particles dissolved in this acid, so this would be dilute. So what is a decimeter? Well, deci usually means 1/10, and if we had a decimeter, 1/10 of a metre or 0.1 metre is 10 centimetres. But if we wanted a decimeter cubed, then the number of centimetres cubed in a decimeter cubed is 10 times 10 times 10, or in other words 1,000 centimetres cubed. Now you may see this written as 1 litre, but litres are not SI units, they're not standard units, and therefore we don't use them. We have to talk about decimeters cubed rather than litres. The units for concentration are moles per decimetre cubed, which means moles divided by decimetres cubed. So the equation to calculate concentration is moles divided by volume. You'll always be given a concentration in the question somewhere, and it will have the units moles per decimetre cubed. So this is an easy way of remembering that equation. So as we said, concentration is usually measured in moles per decimetre cubed. So for example, if I had 8 moles dissolved in 4 decimetres cubed, the concentration would be 8 divided by 4. So the concentration would be 2 moles per decimetre cubed. We need to remember that all volumes need to be converted to decimetres cubed for concentration calculations, and in 1 decimetre cubed there are 1,000 centimetres cubed. So to convert from centimetres cubed to decimetres cubed, you must divide by 1,000. For example, 750 centimetres cubed is 750 divided by 1,000, which would be 0.75 decimetres cubed. Sometimes concentration will also be asked for in grams per decimetre cubed, and that will be the measure of the number of grams in 1 cubic decimetres. To convert from moles per decimetre cubed to grams per decimetre cubed, we must remember the formula that mass equals Mr. Moles. So we take our concentration and we multiply it by our formula mass. So summary so far then. Concentration is measured in moles per decimetre cubed, which is moles divided by volume. To convert from centimetres cubed to decimetres cubed, we divide by 1,000. And to change from moles per decimetre cubed to grams per decimetre cubed, we take our concentration and multiply it by the formula mass. Sometimes we will need to calculate an unknown concentration, and we do this by reacting 2 solutions together. We will know the volumes of both solutions, and we will know the concentration of one. We do this using titrations. You will have covered the method for titration in the C4 video, and in the C3 video we are going to look at how we calculate the concentration. So in this example we have 2 moles of sodium hydroxide reacting with 1 mole of sulfuric acid to produce 1 mole of sodium sulfate and 2 moles of water. We used 19.8 centimetres cubed of sulfuric acid that has a concentration of 0.55 moles per decimetre cubed, and this is sufficient to neutralise 25 centimetres cubed of sodium hydroxide. The question wants us to calculate the concentration of sodium hydroxide. Now this is best tackled using a table as shown on the screen. This will enable us to first of all establish all the different numbers that were given in the question, but then also for us to easily see what we need to calculate. So the first thing is we fill in our table with everything we know, and you can see that I have also remembered to divide my volumes by 1,000 because in the question they're given to us in centimetres cubed, but we need to have them in decimetres cubed. So for both of the volumes I have divided them by 1,000 to calculate them in decimetres cubed. We can now see that for the sulfuric acid I know both the volume and the concentration. This means that I am able to calculate the moles. To calculate moles, we must multiply the concentration by the volume. In this case, that would give me a number of moles of 0.01089. At this point, I am not going to round up my numbers. I'm going to leave that till the end so that the answer is more accurate. Right, I now know how many moles of sulfuric acid I've got. If I look at the equation, I can see that it takes 2 moles of sodium hydroxide to react with every mole of sulfuric acid. If I use an arrow going from what I already know, so I know the moles of sulfuric acid, I'm going to the thing I'm trying to find out the moles for, and on the bottom I put the number of moles that I've come from, and on the top the number of moles that I'm going to. This gives me a fraction with which I can multiply the number of moles of sulfuric acid. If I then multiply the number of moles of sulfuric acid by 2/1, I will get the number of moles of sodium hydroxide. You can see I've entered that into the table. I now have 2 out of 3 values for the sodium hydroxide, and all I need to calculate now is the concentration. Concentration is equal to moles divided by volume. So I take the number of moles, which is 0.02178, and I divide that by the volume, which is 0.025. That gives me an answer of 0.8712. This point, it's worth checking what accuracy they have asked you to use in the question. If they have asked you to do it to 3 significant figures, then in this case we will put an answer of 0.871. These calculations are worth 5 marks in an exam, so really worth getting to grips with. Always make sure that you show you're working out. There's lots of points to pick up along the way. So even if you get the final answer wrong, we can still give you marks for the bits that you've got right. Let's now have a look at molar gas volumes. If we have a look at this balloon, it is 24 decimeters cubed. We saw earlier when we were talking about concentration that when we're talking about volumes, then we work in decimeters cubed. 24 decimeters cubed would be 24,000 centimeters cubed. And in maths, you may have called this 24 litres. We do not use litres in science. These are all the same volume. They just have different units, and the one we're going to focus on is the 24 decimeters cubed. Remembering that 1,000 centimeters cubed is equal to 1 decimeter cubed, which is equal to 1 litre. If we look at these 3 balloons then and compare them, we can see that in every one of the balloons we have 1 mole of gas. In every one of the balloons we have 24 decimeters cubed. The difference is that each of these balloons would have different masses, because we would still look at the mass from the formula masses that we calculated earlier. Let's look at molar gas volumes then. So equal amounts in moles of gas occupy the same volume if we have the same temperature and pressure. Or in other words, 1 mole of any gas at room temperature and pressure will occupy a volume of 24 decimeters cubed. We want to work out the volume of a gas then. If we multiply 24 by the number of moles, this will give us the volume. But don't forget, we need to convert to decimeters cubed. So there are 1,000 centimeters cubed in a decimeter cubed. So if we need to convert from centimeters cubed to decimeter cubed, we must divide by 1,000. So the general rule, 1 mole of gas is 24 decimeters cubed. 2 moles of gas, we times that by 2, that would be 48 decimeters cubed. And 3 moles of gas, we multiply 3 by 24, which is 72 decimeters cubed. So the total volume equals the number of moles times the volume for 1 mole. Or otherwise we could say the total volume is the number of moles times 24 decimeters cubed. This means we can calculate the volume of a gas at this temperature and pressure and know the number of moles of the gas. So if we're asked to find the number of moles of gas, our total volume is equal to the number of moles times the volume for 1 mole. Just as you do with other equations, we'd write out the equation, substitute in the values you already have, and then rearrange it by doing the same operation to both sides. Another way of calculating reacting volumes, here we have the volume of nitrogen a student should react with hydrogen to make 11 decimeters cubed of ammonia. Well, if we know we have 11 decimeters cubed, then using the arrow that we've used before, we're going from 2 moles of ammonia to 1 mole of nitrogen. So that gives us a fraction for our moles, a mole fraction, and we can multiply that by the 11 to find out how many decimeters cubed of nitrogen we would have needed to start with. Yield and atom economy. The yield is the amount of product that is produced in an industrial reaction. The higher the yield, the more profitable the process. We often express yield as a percentage, and the percentage yield compares the actual yield we get with the yield that we would have predicted from our equations. So the percentage yield is equal to the actual yield divided by the predicted yield, and then to turn it into a percentage we multiply it by 100. This will never be a top-heavy fraction. We can never produce more than we would predict, so this would always be a standard fraction. Here we have an example then. You're working in a factory that makes fertilisers. You predict that you make 160 tonnes, but you actually make 144. What is your percentage yield? We use the equation and substitute in the values. Our actual yield was 144. Our predicted was 160. So we divide those two numbers, multiply by 100, and we get a yield of 90%. This percentage will always be less than 100. Atom economy. Chemical companies use chemical reactions to make things that they sell. That means they need to make as much profit as possible. So if they have different routes for producing a product, they want to make the highest yield they can and get the highest amount of product from their starting materials. In other words, they want to achieve a maximum atom economy. Let's have a look at the process of producing ethanol. So ethanol can be converted to ethene, which can be used to make polyethylene. If we calculate the atom economy for ethene, then we have ethanol on our left hand side and we have ethene and water on the right hand side. The first thing we would do is we would calculate the formula mass for each of the compounds in the equation. The formula for percentage atom economy is the relative formula mass of the desired product divided by the sum of the relative formula mass of all the reactants, and then because it's a percentage we times it by 100. So in this case the percentage atom economy would be the relative formula mass of the desired product, which was ethene, so that's 28, divided by the relative formula mass of all the reactants. Well, in this case we only had one reactant, it was ethanol, so that's 46, and then we multiply that by 100 to get our percentage atom economy, which in this case is 61%. It's worth noting that if a reaction only has one product, then the atom economy must be 100%.